Good afternoon. I start this presentation from the motivation part and from the hydrological part, and Ondřej continues to me with technical solution of this this topic. And our talk is about model SMODERP, which we provide in our university, in Czech Technical University, and this contribution is also about the cooperation between two departments, our Department of Landscape Water Conservation and Department Ondřej and Martin is the Department of Geomatics. And the content of this this presentation is motivation from my side, and also about Living Landscape project, which is some volunteering project, and this support, this cooperation, and also something about the SMODERP and the implementation will be continuous. The motivation of this project is basically in three parts. First is that soil erosion by water is a major problem in Central Europe, in Czech Republic directly. You can see in the graph that more than half of arable land in Czech Republic have some risks with the erosion, and this topic is also about the protection of to the erosion. And second motivation is that this process is in small catchments, and this project is focused to the very detail looking to these processes. And second motivation is, as I told, about the small catchment. On the screen you can see that small catchments up to 5 square kilometers. It's covered more than 80% of land of the Czech Republic. And it's, if we look to this processes on the small catchments, we look to these areas, and this is a second. Sorry. And other motivation is to connections to the living landscape. This activity is from the volunteers part, which also would like to protect their lands. And these activities have no connections to some modeling, and the protections you can see in the not work here. And there's some green regular lines, and this is the motivation how this volunteers activity saved or make the protections in the landscape. And these tools which they used work in QGIS, and the second motivation to this contribution to put some hydrological focuses to that. And last motivation is from my side, the scientific motivation to study these processes in the country and provide some technical solutions to design of this technical protection measure, and to reduction the transport sediment to watercourses and reservoirs. And we also look to these processes in the very small scale, in the plot scale. Maybe you can see, I don't know, it's clear to see. On the left, it's start of the surface runoff. This is initial process. In the middle, you can see, I hope, some blue colors, and this blue color is show that second process is surface runoff. And on the right, you can see that move this surface runoff to real processes. This is different things. And we also used some field transform simulator. You can see some pictures. Ondra told me that it's our family album, not family album, it's work album. And we use the rainfall simulator in different variables. Also in the Alpine mountains, we also use this simulator in burned fires, after fires. And we still look to this surface runoff processes. And from this scale, we need to move back from the small scale to catchment scale. And you can see here that we also use some UAVs and long-term field plots to detach where is the rails, whereas we can see the processes. And from the small scale to the field scale and back to the small catchment scales, we need for this shifting some modeling. And for this we used the model SMODERP, and basically the model need this 4 types of the input data, and with some equations and some description of the processes, we can in the model calculate the surface runoff and 2 types of surface runoff, sheet and rail runoffs. And we also make some calibration of the model and calibration on the rainfall simulators, and that you can see how we fit it on the bar soil without the vegetation, and also with some surfaces on vegetations. And calibration is in the sheet flow and the runoff of the sheet discharge. And we also calibrate the runoff on the same place when we detach the rails and we fitted the critical volume of the velocity or shear stress that fitted the rails. And with this, we can build the model in this small scale. And here you can see how the model works. And after this, Ondra continues with this. But basically, we have some inputs data, and the idea is to put this model to different GIS softwares, and from this GIS software produce some preparation data, and in the model it's some looking if we have just sheet flow or the runoff also, or if the runoff going through the stream, because it's different kind of description of the runoff. And it's my last slide. It's how we would like to connect the model SMODERP with the Living Landscape project to how we can support the volunteers which would like to make some protections in the field. And basically, the outputs from the model SMODERP is some additional information to their GIS data, and they can move or put the protective measure where is necessary and not to the regular position. And also we can visualize the effect if they put some protection measure to the volunteers or also to stakeholders. And now Ondra continues with technical part.
Okay. Thanks, Peter. Yeah, so I'm gonna take over for the part about the implementation. And as you can see from the graph, the implementation actually consists of two parts, of something that we call data providers, which prepares the data for the computation, and from a thing that we call the SMODERP core, which is the actual hydrological model that runs some computations and then flushes out some geospatial maps, or some maps in general. As you can see, there are different data providers, as we call these options to run the data preparation. The choice depends only on one thing, which is what you want to do, and then on another thing, and then on another thing. So in the case you want to run only 1D profile, then you have this profile 1D provider. And there was a lightning talk about this one, so I'm not gonna talk about that. Then based on the data you have, if you have just pure GIS layers, or if you have some vectors and rasters, you have to process them using either GrassGIS or ArcGIS data provider. That depends very much on your choice. I guess that everybody wants to use Grass for that here. And in the case somebody has prepared the data for you, you can run the CMD provider, the command provider. About the providers, this is the structure, how they are actually implemented. All of that is implemented in Python, and the providers are using the APIs of like this ArcPy or however it is called, and the Grass scripting library and PyGrass. So the data preparation, I've actually say that, and like the software you use for processing the geospatial layers, and then it gives you some pickle that you can run also in the CMD one, and also for the writing of the data. The core, as I've said, is implemented in Python, and that's the interesting part for the hydrologists, I guess. There is only one dependency, which is NumPy, which makes it quite reasonable in terms of licensing and everything. There are 3 versions, but I'm gonna talk only about 2 of them. There is SMODERP 0.9, but that's like an old school now, and there is SMODERP 1.0, where all the computations of the model were based on the cells of interest. So in the catchment, you don't probably need to run the computation for every cell there, because from some of them there is no runoff or no rain or something. So it was running only on these cells of interest. And then we created something called SMODERP 2.0, where the computations run for the full areas in masked NumPy arrays, and it got much slower, although using the matrices for computations, which sounds quite bad, but then if you run it for bigger data, and then you find out that it's actually much faster than for the small data. So this is an interesting thing that you should actually think about when you test something. If it helped to speed up the process, try to scale your data and try to run your process also on small data and on big data, and then, or okay, this is not big data, but bigger data, as it became a term, and then check if it really got worse or better. And here the time saving for the masked NumPy arrays is surely worth it. Then there is SMODERP Who Knows, which is maybe a new version, maybe not. It's working with an implicit solution of the equations. And we firstly have to find out how is the stability of the computations and how did it get faster or slower, and then we will decide if that was just a dead end of the SMODERP evolution or if it really makes sense. That's done by colleagues from the University of Chemistry or something like this. And the project has some automated tests as it is like a standard in the community nowadays. They run in GitHub workflows, so they are automatic and they assure the computation consistency. So whatever we change in the model, we want to be sure that the speed has changed, but the results are still the same. Or if they are different, then we should consider them better. As there are different data providers, there are also different user interfaces. So there is this QGIS toolbox with a bunch of options where you can get lost somehow. And there is the QGIS module, that's mostly work of Martin, and it has also some nice GUI, but for the tough guys, it also has the command line user interface, the TUI, the terminal user interface, which is surely much nicer. And if you start it in front of people, they always love it. And there is also the command line interface for the really tough ones, where you just start everything from the terminal. And then there is the QGIS plugin for those that would like to send some statistics for the QGIS thing. It's a new thing. It's still considered experimental, an experimental prototype, because it seems to be working. It's really returning something. It returns some blue colors, which look like some nice picture to me, and this person says that it should make sense. But we would like to test it more thoroughly, and then we will consider it a real part of SMODERP. And that's actually it. I'm sorry for the premature ending 1 minute before the time, but I can also thank you for 1 minute. So thank you, Astrid, thank you, Peter, and